Yes. We were talking about the transmission lines, and we're looking up at the properties of the Maxwell equations for a transmission line and deriving all sorts of properties of a transmission lines. And today we will be talking about the waveguides and then about the fiber optics. But before we go on in mathematics, I would like to use this opportunity to bring some of the physics history to you, because the heydays of the waveguides physics were during the Second World War, when the radars become everywhere present, and the problem how to send the signals and collect the signals from those radar antennas which are popping out everywhere in the fields, but also on the battleships, even on the planes. They already had the radar devices on the planes, and the radar operates on the microwave. So there was a question how to send the microwave to the antenna and so forth. We will be talking about the antennas in what follows. So there was a huge effort to understand a complexity of the waveguides physics. And one of the places where this was being studied was, sure enough, MIT. And one of the leading young scientists employed in that business was Julius Schwinger. And that is, the slide shows a book which is called Discontinuities in Waveguides, which is a book collected by Saxon on the notes, lectures and notes which Schwinger had on the waveguides. Remember interesting things about that was that Schwinger didn't know anything about the waveguides. And he came there and had to work with lots of very skillful engineers who were building those devices, and to solve the problems they were unable to solve. And he had two options. The one option was to learn this enormous amount of literature which was existing already on the solutions of the waveguides problems, step-by-step solutions. Remember, there were no computers. The computation, I mean, the game was to do as much as possible by analytic computation without the numerical computation. Numerical computation, which nowadays costs nothing, at that time that was a tremendous performance. We had to employ specially trained people to do these calculations on the hand-powered calculators. It was enormously complicated procedure. So, or to find out a way to solve the problem which were not thought about by the engineers. And that was the path chosen by Schwinger. And he was the first one who used for the waveguides a technique which is called the green functions. So we will finish the lecture by talking about the green functions. This is Julius Schwinger, of course, at the end of his career. He died in 1994. And he developed mathematical techniques for the waveguides, which he later on used in the work on the foundations of electrodynamics. And it was this famous year when three founding fathers of a quantum electrodynamics, Japanese physicist Tomonaga, the Julius Schwinger and Richard Feynman got the Nobel Prize jointly. Each of them was approaching the problems of quantum electrodynamics in a very different way. And each of them developed a different mathematical technique to solve those problems. And the Schwinger based his technique on the waveguides, the mathematics which he learned and developed for the waveguides. And Feynman, of course, in a different way, and Tomonaga was, in some sense, I should say, a conventional physicist. He was just doing a brute force calculation without trying to develop a new method of solving these problems. This was a time where those old school physicists who were extremely well educated in solving differential equations using special functions and so forth, they were doing marvelous without these modern techniques we now have. We will eventually maybe talk about the microscopic theory of materials, like you calculate for example, the electric function for a given medium, and that is nowadays a two-line calculation in a complicated way, using in a very simple way, but even in a complicated situations, using for example, Feynman diagrams technique. But in the 50s, there were no Feynman diagram techniques, and the people like Hungarian physicist Gombas and so forth, they were able still get considerable results by this brute force. So that was Tomonaga, and Schwinger was doing it. Schwinger was a very prolific scientist. He had an enormous number of students, and many today's very top leading coming to the retirement age physicists, they were Schwinger students. But he was also a kind of a not really very pleasant individual, and he ended up in a very strange way. As you might know, in the 90s, there was a phenomenon which was called the cold fusion. Two chemists from a curious place, the university in Salt Lake City, they claimed that they have performed fusion of the deuteriums on a tabletop experiment using heavy water and palladium platinum. And that was an explosion. I mean, it was everywhere. At that time, we even had there was also a time when we, that was 86 or something. This was the middle of a politically dangerous situation in Poland. We have essential martial law. And of course, our generals also joined the thing. And I remember a 1st May parade when next to the head of the junta, General Jaruzelski, there was a physicist from somewhere walking with the glass containing what they claim a Polish cold fusion device. That was completely baloney. Everything was wrong, and it was anyway. I mean, many people, and for reasons which are very strange to understand, Schwinger joined the crew, and he was very much for the cold fusion, and ended up his life writing ridiculous papers trying to resurrect or provide some theoretical explanation for the cold fusion, which were very, very wrong. So we will be talking about the waveguides. I mean, for example, one of the methods of doing calculations which Feynman involved is now called the Schwinger bosons. And it is a technique to solve the complicated problem in the quantum theory of magnetism. And he invented it because he didn't want to go and do a lot of calculations with the special functions, which probably at that time he even didn't know. So he invented the algebraic method of solving these things. At that time, people were very keen of inventing many things. For example, all of you have solved the hydrogen atom. And in the convention textbook of a quantum mechanics, which I understood you have studied, we solved the Schrödinger atom in a very complicated, in order to separate the equation, it's very convenient to do it in a parabolic coordinate system. The hard time is to write down the Laplacian in this crazy coordinate system. Well, to derive the equation for the spectrum, and in particular to understand this peculiar degeneracy of a ground state that it doesn't depend on the magnetic quantum number, that is complicated in the language of Schrödinger equation, but there is a very trivial, almost a high school solution for a hydrogen atom in all details, which is purely algebraic. And that was invented not for solving a Schrödinger equation and a hydrogen atom, but by calculating the properties of the waveguide. So that is the reason why I took the liberty to deviate a little bit from the waveguide, but the physics is the beauty of physics is that it is a building which everything fits whole. I mean, you cannot pull a little piece without destroying the building, but also that it's always possible to use the guidance from that part of physics to solve the complicated problem in the other. So we are talking about the waveguides, and the waveguides are basically transmission lines. We were studying the transmission lines last time, but the important thing is when the wavelength, which I denote here as a lambda, is comparable to the size of the transmission line. Then, of course, the things become complicated, and we have to solve the Maxwell equations, the wave equations, which follows from the Maxwell equations. Remember that from our last week, within this geometry, but keeping in mind that particular property. So let's look up on these two wave equations which we have for electric and magnetic field, and we will be looking at them in this geometry of the waveguide or the transmission line. So the common feature of all those problems which we are going to solve is that they are axial. There is for rather obvious reasons, I decided to denote these radial coordinates going along the waveguide or transmission line as a z. And the transverse dimensions, they will depend on the problem which we were solving. And we are looking for the solutions of the wave equations, assuming that both electric and magnetic field are harmonic in time, they are oscillating, and they have a z dependence, which I had written here as a kappa times z. Now, of course, the kappa is a complex number. The difference between our previous analysis is that now I will look up at what happens when this coefficient kappa is complex. If there's a complex number, then it has a real and imaginary part. And the real part of that coefficient, which is this fancy letter R in LaTeX, that is a damping coefficient. Because if the kappa is real, then the way that the solutions for electric and magnetic field decay when you move in the z direction. But if it is, or if it has an imaginary part, then it is an oscillatory part, and the imaginary part of kappa, well, actually its inverse divided by 2 pi is the wavelength of the wave which is propagating. So if kappa is complex number, so it has both real and imaginary part, then it is this solution would describe a wave which is also damped. And remember, we had an example when we were talking about the telegraph equation, which had the damping due to the, for example, resistivity in a circuit. So now we can now write our wave equations in the way I had written here. That means that the time derivative is replaced by the multiplication by I times omega. So if I have second derivative, then it is replaced by minus omega squared. And I have two algebraic equations, and these are very familiar to us equations, right? That is okay. And I will denote this product of omega squared times the magnetic susceptibility and the electric constant. Excuse me, I forgot to switch off my... For some reason, somebody is calling me and switching. Sorry. So we have these equations, and now I do that trick. Because the problem I'm going to solve has this chosen direction z, which is different, or I will try to look at the phenomena which are essentially different in the z direction and in the remaining perpendicular directions. Therefore, I will split my Laplacian in two pieces. The one which is denoted here as this transverse Laplacian. For example, in a Cartesian coordinates, this is d second derivative with respect to x plus second derivative with respect to y. And there is a second derivative with respect to z. But I have made an assumption that the electric and magnetic field depends in the z direction as a e to minus kappa z, so I can carry out the second derivative with respect to z very trivially, and my Laplacian decomposes into a transverse part of Laplacian plus kappa squared times e. So when I do this, then my wave equation for electric and magnetic field becomes very simple, and they have now the transverse Laplacian, and there is a right-hand side, and the coefficient which is on the right-hand side is the k square, which is the wave vector for the related to the oscillations with the frequency omega, and this coefficient kappa, which we introduced from the very beginning. And I combine these two quantities into something which I denote as a k with sub c. So we have to pay now the attention. We have a k, kappa, and kc. Sorry for it, but occasionally we are running out of letters, right? There was a very famous Russian physicist and mathematician, Bogolyubov, who at one stage of the game had run out of all possible letter, and then he invented his own Greek letter, which he called Belta. He even has a notation for it. It turned out that it is a Georgian. That in Georgia they have their own alphabet. They don't. It's not Russian. It's not Greek. It's not Russian. It's a very special alphabet. I presume there are lots of these alphabets in India, for example. I mean, and which makes life double difficult for foreigners in India. If occasionally they see something written and they learn that this means water, and then they travel 200 kilometers, and it has completely different meaning. And you better don't even ask what. So so we are running out of letters, but sorry for this. Okay. So this is our equation, and now we will be we have to solve it. But remember that we also have the additional part of the Maxwell equation, namely that equation which says that the rotation of a magnetic of the electric field is proportional to the derivative of a magnetic. Rotation of electric field on the right-hand side has a derivative of a electric field, and rotation of electric field has a derivative of a magnetic field. So I can use these two equations, again remembering the derivative with respect to z component is multiplication by this coefficient kappa, and do some algebra, and then I get this complicated equation. I express the transverse component of electric and magnetic field in terms of the z component of electric and magnetic field. And in addition, I have my equations for the transverse Laplacian of electric and magnetic field. So if I take this equation for the transverse and I solve it for z component, then these two equations allows me to solve everything. So this is a complete framework which allows me to solve the Maxwell equations for the problem I'm saying. Well, I still have to remember that there are boundary conditions on the surface of this waveguide or a transmission line, namely they are conducting, so there are boundary conditions for electric and magnetic field, which we have discussed 2 lectures or 3 lectures before. So now, if we look at these equations, we can, and this is a customary notation, distinguish 3 main cases. The one when the z component of electric field vanishes, and these are transverse electric solutions or a transverse electric modes. When the z component of the magnetic field is equal to 0, and these are the transverse magnetic modes, and when both electric and the magnetic field along the z component is equal to 0, and these are called transverse electromagnetic waves. And in several examples, which I will work out now, we will be looking at the special solutions, either this mode or the other mode, because that allows us to pick up silent features of the properties of the waveguides. All right. So let's look up first at this strangely looking mode, namely the one which has z components of electric and magnetic field equal to 0. That is what is called the transverse electromagnetic mode, TEM. All right? In order to be these components to be different from 0, then the denominator in this expression must be also equal to 0. Otherwise, there will be 0 solution. So the only way how we can find out that for EX and for EZ and HZ equal to 0, transverse components are different from 0, this coefficient K sub C must be equal to 0, and that means that the kappa square plus K square also have to be equal to 0. So if this is happening, then because K is real, then kappa is purely imaginary, and I can solve it, and that means that we are having a wave. For transverse electromagnetic mode is a wave which propagates, and it propagates with the speed of light. So we have solved, it looks like the TEM mode is just an electromagnetic wave, a light wave, but of course with the velocity which depends on the property mu and epsilon. So what happens further? Well, we have now for Kc equal to 0, then our transverse equation turns out to be Laplace equation, because the right-hand side is 0. And we have a waveguides with a proper boundary condition, and we have a Laplace equation to solve it. So it looks very simple. We have turned the problem of a waveguide, at least for the TEM wave, into the solution of the Laplace equation with a proper boundary condition. But since the electric field, the surface of the waveguide is equipotential, then the electric field vanishes on the surface. And the Laplace equation has a unique solution. And if it vanishes on the boundary, it vanishes everywhere. So if I have a waveguide which is empty inside, it only has a wall, then the electric field and the magnetic field vanish. So there is nothing is propagating. So if I want for some reason to have these TEM waves excited in my waveguides, then I have to do something, namely I have to put up an addition boundary in the middle. If I put an addition boundary in the middle, then depending on the boundary, the solution, on the boundary conditions on it, the solution of the Laplace equation might not be identically equal to 0. So the TEM wave, which are different from 0, they can only exist if there is a wire or something which is inside of my wave. All right. So let's continue, and let's try now to solve a very typical waveguide problem, which is a kind of a rectangular box. It's a long pipe which is rectangular, and it has a width which I conveniently denote by W for width, and which has a height which I denote H for a height. So now we have to solve this problem, and I solve it for transverse magnetic modes. So I have the equation for the electric components, X component, and the Z component is in the direction along my box. And what are the boundary conditions? Because it's a piece of metal, then the boundary conditions on all walls are that the electric field is equal to 0. So what is the solution of that equation with these boundary conditions? And remember kindly that solution. It's a product of a sine function. Because if you differentiate once the wave function, sine, then it comes a cosine. And the derivative of a cosine is minus sine. So that generates me the minus sign on the right-hand side. And this I have to do in both x and y directions. So the solution of my equation, which fulfills the boundary condition, is that of that form. Well, but because it has to vanish on the walls, then the sine function in each direction has to vanish on the walls. A sine, as you remember, vanishes when the argument is 0 or pi. Well, actually 2 pi and so forth, but it repeats periodically. Therefore, we immediately can solve that for the wave vectors kx component kx and ky, and this is the solution. The wave vector component kx is proportional to the pi, and that is just m is a natural number, and the same with the y component. And the wave vector k square is a sum of those two numbers. So we have solved for the magnetic field, and since we have now the wave vector, then we can associate with it the frequency. And since the k has two labels, m and n, two natural numbers, that is like, I can call them quantum numbers. These are two natural numbers which tells me what are the modes. So I also have a frequency which are numerated by these two numbers, m and n. And they are related to each other by a square root of the mu and epsilon. So I have a characteristic frequency. So if I have this rectangular waveguide, then the TM wave which propagates in it is an electric field which has a set of frequencies available, modes which are numerated by the integer numbers. So now I can do a couple of algebra tricks. I can calculate my propagation factor kappa. Remember, kappa was the thing which tells me how the wave propagates along the z direction. So the kappa square is a kc minus k square. So I can turn algebra and find out that this coefficient is kc square times a product of this ratio. So it turns out that kappa becomes changes sign depending whether frequency of the mode is larger or smaller than this bandwidth number omega m and n. If the frequency is smaller than omega m n, then the kappa is purely real, and since the dependence of the field along the z direction is e to power minus kappa times z, that means that this is a damped solution. It's not propagating along this direction. But if the frequency is larger than this band frequency, then kappa is purely imaginary, and we have a wave. So in this kind of a waveguide, there are waves propagating along this direction at sufficiently high frequency. Great. And of course, this is easy to solve in a rectangular case. And the obvious question is, how does it look like if this is a cylindrical wave? And then it's complicated. I can solve easily for the wave, and if I had a circular waveguide, then it is obvious that I should use a cylindrical coordinates. So I have a radial and polar coordinate and the z direction. And this is the solution for the field, which is given as a combination of special functions. And there are these Bessel functions and Neumann functions. And since I don't know how many courses of mathematics you had and whether you know anything about the special functions, but those are those functions Schwinger hated. So he invented his own methods of solving the equation. But the Bessel functions are oscillating and the Neumann functions are exponential. But we will not use them unless it is really desperate situation. And the dispersion relation is extremely complicated. So the only conclusion which is sort of convenient to remember, that for a transverse, for this rectangular waveguide, we had this band frequencies omega mn, which had been some kind of a border frequency. Above them, the wave propagates, below them, the solution is damped. Okay? For the frequency is related to the wavelength. So I could have used not this expression on my previous slides in the k omega space, but in the lambda omega space. But I was too lazy to write in an additional slide. So I only use one. But for the cylindrical waveguide, it is more convenient to remember that there is also the critical frequency, but it is less convenient to think about that frequency, but rather think about the critical wavelength. And that critical wavelength is, roughly speaking, equal to the radius, to the ratio of the radiuses of this wave. All right.
What was I?
Because you had to have something in middle, because otherwise the Maxwell's solution would be zero. So you had this core, okay? And I mean, these things were built to do something. They were not the problems invented for solving differential equations. They had to be used for something, particularly for sending the waves with high frequency. So the microwave frequency from 1 to gigahertz, then the convenient, the size of the system which can carry them is from 10 centimeters to the 1 millimeter. So since in the modern technology we have to increase the frequency even more, then this waveguides we have discussed will have two dimensions which are smaller and smaller. So we will have to build up a very sturdy and microscopic object. That's very engineeringly impractical. So the engineers had a problem, how to guide the high frequency microwaves, electromagnetic waves, since because metal construction were very impractical. Even the little pipe with a very small diameter will bend easily and broke and something. So it turns out that you have to invent something else, and the invention was fiber optics. And that is what revolutionized the technology. We now have fiber cables under the oceans, which are slightly different from what I will be discussing in a moment, in the sense that they are not, dielectric properties depends on the frequency. Therefore, they are nonlinear. And if they are having if the dielectric constant of a material depends on the point in the medium, that is called dispersion. So these are dispersive and nonlinear media. And if they are nonlinear and dispersive, then we can build up the waveguide where the nonlinearity compensate dispersion, and then as a little devil out of the glass of wine, it jumps mathematical beauty in terms of a soliton, a special kind of solutions of waves which can propagate without changing its shape over incredible distances. We can send the giga bits of information through the oceans in the form of solitons without any need of the amplifying the signal over those distances. Solitons are curious phenomena. Soliton means solitary wave, the wave which is separated. They were discovered by the sailors, and there are many of this discovery. The one of the story is that there was a certain British gentleman who was riding on a horse along the channel somewhere next to London, and there were fishermen carrying a barge over the channel, and all of a sudden they moved the barge, and the barge all of a sudden created a dip in the water, which propagates without changing the shapes along the channel. And this gentleman wrote a story that he followed on a horseback, that strange phenomenon, and eventually he got tired for riding, so he stopped and it continued. But then he went back home, and since the British gentlemen in the 19th century were well educated in mathematics, he sat down and solved equation which describes the waves in the channel. This kind of equation is called the Korteweg-de Vries equation, and found out that solution which we now call a soliton. And this was known by hydrodynamicians for years and years, and all of a sudden it was again discovered by engineers making waveguides, and again was discovered by the physicists in the 80s, when the nonlinear physics becomes very popular, and turns out that solitons everywhere. They are in the quantum optics, they are in the cold things. These are the non-changing shape waves which propagates when the dispersion is compensated by the nonlinearity. So how do we create those things? Let's first discuss the following problem. We have our waveguide, but we put in the middle a slab which is, contains a dielectric constant which is different from the vacuum. So we have a box where we have a slab of dielectric medium, and we will be sending electromagnetic waves in that kind of geometry. The trick is that we have a boundary conditions on the surface between on the boundaries here and there, and of course we have to, and we are looking for a possibility that the wave will propagate in a slab of a dielectric medium, so it has to decay when we move away from a slab of a dielectric in both of those directions. The thickness is h, and the waveguide is in the screen, so that's the z direction, and nothing depends on the x direction for a while. So we are only looking at the solutions which depends on y and move in the z direction, and nothing depends on its translation invariant, as we will say, in the z direction. So what we have to solve is, for the now transverse electric mode, is the equation. Nothing depends on z, nothing depends on the z, its dependence E2 minus kappa. So it's multiplication. There is no direction, there's no dependence on x, so we can neglect we can put the derivatives with respect to x component to 0. So our Maxwell equation turns to the equation which is written here. And now I will try to solve it, making the assumption that this coefficient kappa is I times beta, and therefore this we will be playing now with the complex number beta instead of kappa. I apologize for it, but that is a convention to study the fiber optics. All right, so let's see what happens. The transverse electric mode is periodic inside the dielectric slab and has to be dumped outside. This is again the picture. So for the y, which is larger than h, the modulus of y larger than h, this equation has to look like the first equation on the slide, and inside of the slab it has to be propagating, so the coefficient has to be negative. So if I do this, I can easily solve this second order differential equation, and the x components of a magnetic field outside of the slab is damped, and it is propagating within the slab. So now I have two solutions, and what I have to do, I have to apply the boundary conditions. And if I apply those boundary conditions, then I get a relation between the coefficients a and b, these amplitudes, and this coefficient is that a is equal to b times the cosine of the coefficient b. Remember that b is this coefficient and a is this square root. So a and b are given coefficient, but I mean, if I wrote here everywhere the square roots, I will get mad in typing them in LaTeX. There is a certain limit of my indulgence in writing those equations. Okay. Transverse equations we can derive from our already known equation. So I can calculate the x component of the electric field. And if I combine this everything, I have the electric field in the x component, which is for the y larger than h, for y less than minus h, so it's outside of the slab. And I also have the oscillating function within the slab. So now I have my boundary conditions. So if I combine this, then I have the equation that a capital A divided by small a is equal capital B divided by small b times the sine BH. And that is, if I use this previous boundary condition, then I get the relation that B divided by A is a tangent over B and H. And that's complicated. That is because the tangent is a periodic function, so there are multiple solutions for it. We don't have a one solution. We get the relation between these coefficients, B and A, but it depends on the bands because it's periodic. The tangent is periodic function. All right? So I have a B and A, and I also have a definition of what is A and B. So if I use the definition of these coefficients A and B, then I can combine this coefficient and I find out that A squared plus B squared is equal to the K1 square minus K0 square. And because K1 is proportional to K squared is proportional to the dielectric coefficient, therefore the A squared plus B squared is proportional to the difference of the dielectric constant outside and inside of inside of the slab and outside. So if the outside is a vacuum, that is epsilon 0, and inside there is a dielectric constant of the thing. So as you see, in order to have the coefficients A and B real, then the epsilon 1 must be larger than epsilon 0. So now I have two equations for those coefficients. B over H is equal to tangent, and it has this multiple solution by the tangent. And this A plus square plus B square, it's a circle. So intersection of these two numbers give us the modes which can propagate in the fiber optic. And that is the basic equation for the fiber optics. We can propagate modes very, very fast inside of that. This solution is necessary because it turns out when we will be talking about the optics that it can be reformulated in extremely simple relation concerning the diffraction coefficients, but that will come when we will be talking about the optics. So that is now, we had the basic mathematics of a fiber optics, and now how it is being made. It's made that way that there's a core which has a certain dielectric property, which is surrounded by a clad, as they call it, is a medium which has a lower dielectric coefficient than the core, and then there is something outside which prevents it from being so easily destroyed. And the fiber optics is something which changed our world, so to say. With this, because of the glass, optical glass, is most transparent for the infrared waves, then it's possible now to build up the fiberglass, which the amplitude decays by a 1,000 of its value over a distance of 150 kilometers. So that is something completely incredible. And in addition, a glass is cheap. Glass is enormously cheap because it's a silicon, and the silicon is everywhere. You get your shovel, go into the garden, and you get yourself a material out of which you can make a fiber optics. The problem is that it is easy to vandalize it. So in a modern world, there's an easy trick to prevent the long-distance fiber optics from being vandalized. Namely, the long-distance fiber wires are now attached to the high-voltage lines connecting cities. Well, they are very high up there. the 60 hertz, 50 in Europe, hertz of the alternating current is so separated from the frequency of a light that it's completely irrelevant. And if somebody climbs up there to steal the fiber optical cable, well, it's not really surviving long. So it's very easy. I mean, in the cloud of the high voltage cable, there's a bunch of the fiber optic. Actually, I mean, if you now go in Warsaw and dig a hole, the probability is almost 1 that you will dig out the fiber cable. When we were building up a Copernicus Science Center, I mean, we got the plan of how, I mean, you need to dig a hole, right? So you had to knew where are the cables and so forth. And all of a sudden, a optical fiber was found. And nobody was willing to accept whose wire that is. And the only thing we learned is that under no circumstances we are allowed to cut it, because it's probably very important. So it was easy to know that this is owned by some very important institution, right? And the engineers who were building the center made a real game. They dig out that wire, put up on the poles, and they were driving this heavy building equipment without touching that wire for 2 years. And then at one day, 2 gentlemen show up and they said, well, it's no longer necessary, we can cut it. And they just cut it, and they left us with a few hundred meters of the wire. So that was my practical experience with the fiber optics in my life. But as I said, we are now finished with the green functions, and let me just outline you what are the green functions. So suppose you have a simple equation, linear equation, a derivative of a certain unknown function y is, and the operator, derivative operator, for reasons of a generality, I will call L, okay? It's a linear operator. So I want to solve the equation Ly is equal to 0 with the proper boundary condition, and I took a liberty of using a one-dimensional case, so I make the solution very simple. The y at the 0 and at 1 is equal to 0. So this is very trivial. To solve, everybody knows that the solution is that y is equal to 0. But I can make it difficult. In German language, one say, warum einfach, wenn man kompliziertes machen? And why is to solve something simple when you can complicate it? But so we complicated this very simple case, but it turns out that we learned something very interesting about it. So I have I have a set of functions, and I make the set of functions into the vector space by defining how I multiply these functions. And that is a definition of a scalar product between these two functions. It is very easy to check that it fulfills all the rules of the scalar product, so everything is fine, and that is my definition. So with that, I can define the adjoint operator. This is the operator which, instead of acting on a function g, acts on the function f. And this is, in my case, a minus d over d. Well, I'm sorry, there's a tremendous mistake. It's not y, it should be derivative with respect to x. Sorry. So this is wrong, that should be x here, sorry. And that, of course, comes out from the partial integration by parts. But the boundary condition for a joint operator is not the same as for normal operator, so the solution for the equation L dagger equal to 0 is equal to 1. That means that the scalar product of that solution with the function f is equal to 0. All right? So now I can solve my inhomogeneous equation. I want to solve now the inhomogeneous equation. That is equation L times y is equal to f. And the solution is very simple. Y is the integral of a function f. And I can write it in a complicated way. Namely, instead of having an integral from 0 to x, I write it as an integral over all system of the function, unknown function f, this right-hand side of my equation. And there is a beast sitting inside, which is called the green function, and which is denoted by g. And it's a function of two variables, x and psi. And it's very trivial to see that for our particular case here, this function g is a Heaviside function, which we had discussed. The function which is called theta, and that is this function which is defined. It's 1 when x is larger than psi, and it's 0 when the x is smaller than y. So it's discontinuous function. Its drawing is shown here. These red dots denote the function. And in some sense, it's not a decent function because it's discontinuous, right? It is continuous function which is discontinuous in one point. And that was the problem of Mr. Heaviside. For him, it was completely fine to use such a functions. But at that time, mathematicians didn't like this continuous function. And in the history of mathematics, there is a very famous letter written by the distinguished mathematic Stokes to his colleague Peano in France, where he says that he turns his back to this awful space of the continuous function, of these continuous functions which are not differentiable. They didn't like it. But what happens if I apply the linear operator to the function g? Then, because L is a derivative, I have to calculate the derivative of this function. And of course, this function is discontinuous, and the derivative is everywhere 0, except this very one point where, who knows what happened. You don't have a method of calculating, and that is the famous Dirac delta function. And that was all discovered by Mr. Heaviside. And Mr. Heaviside had this tremendous discovery. I took the liberty to show the same picture again. But he said that it is experimental science. He had to define this operation. And later on, Dirac picked it up. And in the 50s, a French mathematician, Laurent Schwartz, finally and the Polish mathematician, Professor Mikusiński, they finally built up a correct mathematical building where those objects like the theta function and Dirac delta functions were having a proper mathematical definition. They are called distributions. And there was a famous book by Laurent Schwartz, The Theory of the Distribution. And basically, that is a mathematical proof that Mr. Heaviside had right. He knows how to solve the problem. So that's the beginning of green functions. And of course, who cares about the first order differential equation? We can solve everything very easy. So I promise I make it complicated. I have made it complicated. And next time we will be discussing that for a second order differential equations, particularly with relation to our rectangular waveguide. And as you will see then that it is much more convenient to use a green function than to solve the differential equation. Thank you very much.